Alright, so this video is about sound. Sound is the last of the major kinds of waves that we're going to talk about. We've talked about waves in general, waves on water, light waves, and now it's time to talk about sound waves. So the first thing to mention is that sound is produced by vibration. So vibration of some physical object is what produces sound, and it is a kind of a wave. It carries energy. All right. One important thing is that sound requires a medium in order to travel. It cannot travel through a vacuum. It must travel through either a solid, a liquid, or a gas. I suppose also a plasma would work, but we don't typically encounter plasmas on Earth. So basically solids, liquids, and gases. Sound can travel through any of them, but it requires some physical medium in order to travel. It cannot travel through the vacuum of space where there is no solid medium. Alright, so that's the first thing. Vibration. So something vibrates. Something physical vibrates. You could have a guitar string, like we have right there, that's vibrating, and that vibration produces a sound. You could also have vehicle speakers, perhaps, like these expensive add-on speakers in somebody's trunk. The cone inside would vibrate in and out based on an electromagnet that moves, and that produces a series of sound waves with certain frequency, changing frequencies to produce the music. So the oscillation of these speakers back and forth is what produces the sound in that case. So that's a vibration as well. Alright, so let's talk about a bit more. Here we have a visual representation of what sound might look like if we could see the actual waves. So here it's graphed. It's important to note this is not what sound would look like. This is what the pressure of the sound would look like if you graphed it. So this is a graph of sound pressure levels. Compressions are the high peaks and rarefactions are the low peaks. Now this graph represents what's actually happening here, and these would be the air molecules if we could see them. So as perhaps in this case a speaker oscillates back and forth, back and forth, back and forth, this speaker cone oscillates, it pushes and pulls on the air molecules, and that sends pressure waves outward from the speaker. So when the speaker pushes forward, it makes a compression of molecules by pushing the molecules closer together. Then when it moves back again, it creates a rarefaction or a spread out region where the molecules are pulled further apart. So you have a series of compressions, and rarefactions. So this is a compression, and this area here between compressions is called a rarefaction. And then, as we mentioned, those are graphed then on the sound pressure graph up above. So this compression corresponds to this peak in sound pressure. Pressure is highest in the compression. And then this trough here would correspond to a rarefaction where the pressure is the lowest. All right. So sound waves are longitudinal. They oscillate parallel to the direction that they travel, which means that the oscillation goes back and forth in this direction, and the wave also travels in that direction. So the oscillation is parallel to the direction of travel. All right, that's in contrast to a transverse wave where the oscillation might be up and down when the wave is traveling this way or whatever. All right. Now a little bit about sound frequencies. There's a certain range of audible frequencies for a healthy young person or a healthy, typically average-aged person. The lowest frequency they can hear is about 20 hertz, and the highest audible frequency is about 20,000 hertz. So just remember 20 to 20, right? 20 hertz up to 20 kilohertz. That is the range of frequencies that is audible for a typical healthy person. All right. As you get older, you lose the high end and a bit of the low end as well. So your range of audible frequencies gets smaller as you get older. Just normally, and also if you have damaged hearing, you would lose some of these frequencies as well. But that's the typical range of audible frequencies. Anything below this, you would not hear it, pretty much, and anything above this, you would not hear it. It would not even be like a buzzing in your ear. It would literally be inaudible. You would not be able to hear it. All right. You need to know those numbers. They come up fairly often in test situations. All right, and that brings us to our last little topic for this introductory video. Some of you have probably heard of an ultrasound, which is where an image is generated of the inside, typically of a woman, but it could be the inside of any person. Maybe they're using an ultrasound to look for injuries or something. Proper functioning of organs, I don't know, but typically ultrasounds are used to check on the status, the health of an unborn child, or a fetus, as the medical term is called. So the word actually refers, ultrasound, that word refers to any sound that is higher pitched than human beings can hear. So ultrasound, ultra means more or higher, higher than sound. So sound, we typically talk about things that we can hear, that are audible. So ultrasound would be higher frequency than what we can hear, so higher than 20,000 hertz. All right. So in common usage, it's used to create an image of an unborn child, basically by reflecting those waves off of the internal structures. So the waves pass through the outer layers of the woman, her skin and her muscles and so on, and then they bounce off of the child and come back, and they're detected by the machine and translated into an image. So anyways, that's a pretty cool application of sound. It's kind of like sonar or echolocation, which we'll probably mention more about those in a future video. That's it for this introduction, and I hope it was helpful. Thanks for watching, and we'll see you next time.